Hello there. This video is on section 7.8, and I'm going to be demonstrating how to use limits to find improper integrals. So first of all, we need to know what an improper integral is. It's basically a integral with numbers on the integral sign, so it's called a definite integral, which basically represents an area. So we're going between x's 2 and 5 or something like that. So that makes an interval, well, an interval of x values between 2 and 5 or whatever is specified. An improper integral is one of these definite integrals where one or more of these points on this x interval are undefined. They make the function not calculable. So famously, things that are not calculable are dividing by zero, square roots of negative numbers, log of zero, things like that. If that interval contains undefined function values, we're going to try to use limits to find a value for that integral. And this is the idea behind section 7.8. So let me demonstrate some examples for you. And of course, I have my lecture notes available on Canvas if you'd like to download those and take notes and write along with me. That would be great. So I have example A right here. This goes from 1 to infinity. Infinity is not even a number. It's not going to be something we can calculate in an integral. So this is a simple example of when something on this interval isn't really going to be defined. I can't really plug in infinity into any function whatsoever. So we're going to try to use improper integration to use a limit to figure out if we could determine the value of this integral. So the first thing we do is we need to make this a number. So we're going to use a placeholder for the number, usually like A or B. I'm going to use B as a placeholder. And what we really want is B to be infinitely large. So I'm going to be doing that by writing a limit. And we want B to get as close to infinity as possible. That's a limit as B approaches infinity of this exact same integral. Oops, there's my dx. All right, so now we can antidifferentiate 1/2 to the x. So how do we antidifferentiate 1/2 to the x? Well, believe it or not, this is one of our formulas. You may remember how to integrate e to the x. Most people remember that because it's just the same thing. Well, e to the x is, well, e is a number. 2.718, but it goes on and on. It's a number, kind of like pi. 1/2 is a number, a little bit easier to write, 0.5, but it's just a number to an x. So we do have formulas for antidifferentiating a number raised to an x. If you're unfamiliar or don't remember that, you can just go back to the formula sheet I have, or any formula sheet. And let's see if I can find it. Here it is, number 4. Any number raised to the x, so n is a constant, so a constant raised to the x has an antiderivative of that constant raised to an x, so it repeats itself just like the e to the x repeats itself, but we get this divided by ln of the number. So we need to divide it by ln of 1/2 in this case. All right, so this is going to be the same thing, 1/2, let me go back to my blue, 1/2 to the x, and then divided by ln of 1/2. And we don't really need a plus c if you remember. I mean, there is a plus c here. Let me just fix this 2 so it looks like a 2. There is a plus c. Sorry, just trying to make it very legible. But because we're plugging in numbers, we're plugging in 1 and b as our limits. The plus c is going to disappear, right? It's going to be a plus c and a minus c. So you may have seen this from previous homework assignments. When doing a definite integral, you can write the plus c. It's just going to subtract off or cancel out. So a lot of people just not write it anymore. All right, so let's see what we get from here. So from here, I have my limit I have this integral. I have to plug in the top limit and the bottom limit and subtract. So when I plug in the top limit, that's b, I get 1/2 to the b divided by ln of 1/2. Don't get scared of ln of 1/2. ln 1/2 is just a number. You know, plug it into a calculator, it gives you a number. And then minus when I plug in 1. So 1/2 to the 1 over ln of 1/2. So there I've plugged in the top and bottom limits and subtracted. Now I have to take the limit as b approaches infinity, and you have to go back to your, calculus 1 class for, more practice about limits. But in this first expression here, b only occurs right here as an exponent. And 1/2 to the b, 1/2 times 1/2 times 1/2 times 1/2 gets smaller and smaller and smaller. If you remember that, any decimal less than 1 raised to the infinity is going to tend to 0. So this tends to 0 over ln of 1/2 minus when I plug in, there's no b's here at all. There's no b's at all in this expression whatsoever. So I get 1/2. There's no place to plug in b. I just get the expression. I get 1/2 over ln of 1/2. And this part is just 0 because 0 divided by anything is 0. And this part is going to be whatever negative 1/2 over ln of 1/2 is. And you could just leave it that way. I mean, I like precise answers. And so negative 1/2 over ln of 1/2 is a fine answer. A lot of people don't like this. They say, I want a number. So let me put it into my Desmos, negative 1/2 over ln of 1/2. I have some stuff prepared here. So negative, let me just hide this. There we go. Negative 1/2 divided by ln of 1/2. And what is that? That is 0.7. I mean, it's a irrational number. I'll round it to 3 decimal places. Like I said, I prefer the exact value, but I think a lot of students are uncomfortable with answers that look like this. So you can convert it into a decimal. Positive. There's no negative. 0.721. 0.721. So I'll say approximately 0.721. So this integral, which had an infinite interval for x's went from 1 to infinity, that area is finite. The area under the graph above the x-axis between 1 and infinity, that total area adds up to 0.721. And so we call this converges, which is a term you may have heard before, because it actually equals a specific number. So the specific number is negative 1/2 over ln 1/2, which is approximately 0.721. So we say this integral converges. It has a finite area. And let me give you just a visual. I prepared a visual here on this idea. So I have here at the top the function 1/2 to the x. That's the function 1/2. I've zoomed in a bunch just to make it easier to see, but that's the function of 1/2 to the x. So there's what the function looks like. And then we're going to try to find the area. Now we're starting at 1, so I don't really need this stuff, around 0. I really start at 1, but I'm just going to put this over here just so we can have some perspective. I'm going to be using rectangles to approximate the area, just to kind of visually show you what's going on. So for this first interval, or first part of the interval from 1 to 2, I'm going to make a little box here. So this box has an area which is bigger than the area between the function and the curve. The area between the function and the curve is down here, and this box is definitely bigger than that area. So the area of the integral is going to be smaller than the area of this box, at least in that little space right there. What is the area of this box? Well, it's a rectangle, has a width of 1, has a height of 0.5. So this is 1 by 0.5. That's the area of this box. I'll do the same thing with the next interval from 2 to 3. I'm going to make a box. It has a width of 1. It has a height of, well, half of this is 1/4. So this is going to be 1 times 1/4 or 1/4. So the first box has the area of half. Second box has the area of 1/4. Third box is going to have an area of 1/8. So we have a half plus 1/4 plus 1/8. The next one will be a 16th. So that area of a half plus 1/4 plus a 16th, etc., is going to be bigger than the area between the function itself, the green function, and the x-axis, right? So I'm finding a larger area. So let me go back to my little notepad here. So we know that, for example, we know that this area here, from 1 to infinity of 1/2 to the x dx, and is going to be something we're going to use and compare to the 1/2 times 1 plus 1/4 times 1 plus 1/8 times 1, right? These are the areas of the boxes. Or in other words, 1/2 plus 1/4 plus 1/8, etc., right? So that infinite sum of fractions is going to be larger. Remember, the green graph was underneath these boxes. So this integral, the thing that we're trying to determine, I guess we already determined using limits, is definitely less than a half plus 1/4 plus 1/8 plus the 16th plus the 32nd, et cetera, et cetera. But this sum of infinite fractions is classically equal to 1. If the door is 1 foot away from me and I walk to the door, I first go a half a foot, and then I go to 1/4 more foot, and then I go 1/8 more foot. I mean, you can divide these up into as many fractions as you want, but I'm getting to the door, right? It's not like I don't get there. So it's also not going to be infinitely far. The door is definitely 1 foot away. So this sum right here, it classically adds up to 1. And interestingly enough, in this class, we're going to actually do this mathematically. We're going to do it very carefully and show why this has to equal 1. But for now, hopefully you could use your ideas that you've learned previously about why this has to add up to exactly 1. All right, I'm going to pause my video to fix my pen is what I'm trying to say. So this is, equal to 1, which we will show. So anyway, so I just want to demonstrate visually that this area is finite. In fact, it's less than 1. In fact, we know it's approximately 0.721. All right, I'm not going to go into this sort of deep intuition dive for the rest of the problems, but I did want to show you that on one of them, so you have an idea of like what's actually happening here. We're trying to find an area. We're trying to find if it's finite. This first one is finite, so we say it converges. It converges to this, this number, or approximately this number here. All right, let's do a couple more examples. Example B I have here. I have an integral from 1 to infinity of 1 over x dx. So we're going to do the same thing. Limit, choose a letter such as A or B or C or something. Take a limit. We go from 1 to B. 1 over x dx. 1 over x dx is another one of those known integral formulas on our integration sheet. The integral of 1 over x is ln x. And we need to evaluate this from 1 to b, and then take the limit. So you have to keep writing the limit thing. A lot of people forget. So keep writing the limit thing to avoid yourself losing points for not writing it properly. So I'm going to put in the b. B goes in for x. And then I'm going to plug in the 1, subtract, and then find the limit as x goes to infinity. ln1 is 0, so this is actually going to go away, but what the key thing is, what happens when I plug in infinity here. So what happens when this thing approaches infinity? Well, ln of infinity, ln, you have to sort of go back to your pre-calculus stuff. Ln, the natural log function, like any log function, goes like this. This is what the natural log function looks like. It increases forever. So it goes up and up and up and up. Sort of like an exponential, goes up and up and up, but it's upside down, kind of. It goes up and up in a concave down way, but it never reaches a peak. It never goes down. It never does that. It just keeps going up and up and up, up. And so ln of infinity gets bigger and bigger and bigger. Or ln of x gets bigger and bigger and bigger as x gets closer and closer to infinity. So this thing here tends to infinity. Ln of an infinitely large number is an infinitely large number. So we get infinity minus 0, but honestly, it could be infinity with anything else. And this we say does not equal a number. This is, I'll just write it out, does not equal a number. So what do we call that? We call that divergence. So that's our name for this. So we would say this thing, the answer here for this integral from 1 to infinity of 1 over x dx, we would just say it diverges. And when you're doing the homework, you'll see in the instructions, you'll say, tell me if this thing converges or diverges, right? And in this case, you would just say diverges. If it converges, you can tell what it converges to, like in example A, but if it diverges, you just say that it doesn't add up, and you leave it at that. It's an easier answer to type in. All right, we'll do some more trickier, more difficult examples. They don't get too much more difficult, but they definitely get a little trickier. So I'll show you a few of those, and that'll be the rest of the video for today. All right, so example C, we're going from 0 to 16. That is not going from like something to infinity. There's no infinity here. So on first glance, you may just say, okay, well, let's just go for it. But the thing is it doesn't have to be infinity as your limits on x. It doesn't have to be your interval going to infinity. It just has to be something which is undefined, right? So remember, an improper integral is some sort of definite integral where one or more exponents in the interval make the function undefined. So if we look carefully at this function, maybe I'll zoom in so you can look carefully, right? So there's the careful look. You'll notice that this is a fraction. And if we have 0 in the denominator, we would have 1 over 0, which is not calculable. And in fact, there's a 0 right here. So the left-hand endpoint, 0, is not calculable in this function. You can't plug in 0 into this function and get any answer. So therefore, this is an improper integral, and we're going to have to use a limit. So I use a limit. We want 0 to be the point. I'm going to use a is equal to 0, or a approaches 0, which seems odd because I used b before, but you'll see the reasoning for my madness in a bit. So instead of going from 0 to 16, I'll go from a to 16. And then this thing right here, I'm going to write it in proper mathematics ways by using fractional exponents. In fact, I'm going to use a negative because it's in the denominator. So negative 1/4 is the same as over 4th root. So this is the limit of this improper integral. We're going from a to 16. A I'm going to use for like the bottom limit, and I'll use b for the top limit, just to try to keep track of it in my mind, but you can use whatever letter scheme you want for these problems. All right, so now I need to do my anti-differentiation and find out to see if the area is finite or not, if it converges. So antiderivative of a power, x to a number, that's again one of our known formulas. So I add 1 to the number. Negative 1/4 plus 1 is 3/4. And I divide by 3/4. So that's the n1 over n plus 1 dealy thing. And I go from a to 16. And that will give me, well, I got to plug in the numbers, right? So I got to plug in 16. So 16 to the 3/4. I'm just going to write this as 4/3 if you don't mind. so that it's a little easier to write. And then minus, I have to plug in a. So I get a to the 3/4 times 4/3. So that's when I plug in the numbers, that's what I get. Now I have to find the limit. So this first guy here doesn't have any a's in it, right? So let me down a little bit. There we go. So this first thing right here, there's no a's. So I can just compute this normally because the limit doesn't matter. There's no a's in the expression. So I get 4/3. And if you compute 16 to the 3/4, you get 8. You can check that with your calculator, or you can know that the 4 through to 16 is 2, and 2 cubed is 8. So there's different ways of knowing that that's equal to 8. Over here, I have 4/3, and this thing is going to be 0, because I'm going to be plugging in 0 to the 3/4 power. 0 to the 3/4 power is 0. So all of this stuff right here goes to 0. So my answer is going to be 4/3 times 8, which is 32/3, and we say it converges. So this improper integral, which went from 0 to 16, we used the limit, and we can show that it actually converges. The area is equal to 32/3. Okay, so let's see a few more examples before we call it a video, call it for this section. All right, so here I have more complicated thing to integrate, but that's not really the tricky part about this. If we examine this thing, and you're going to have to sort of really take a good look at integrals now, because a lot of times we just like start doing our formulas and doing our routine and we get an answer, but you're going to have to look very carefully to see if it's an improper integral. This one, if I put 0 in the denominator, I can't do 1/0, right? That's not going to work, right? And so if I have a 0 here, it's no good, right? 0 square root of 0 is 0, and so that would make it undefined. But that's not really a problem, because 0 is not part of our interval. Our interval goes from 1 to 16. It doesn't have anything to do with 0. So whether or not 0 makes the thing undefined doesn't come into play, because we're only trying to find the area between 1 and 16. We're not trying to go from 0 to 16. So this on its face looks fine because there is no 0 in the interval. The problem is that there's more than one thing in this interval. And for this other part right here, some of you may have noticed it already, this other part right here, x equals 16. When x equals 16, you get 1 over, you get the square root of 16, which is 4, and then you get square root of 16 minus 4, which is 0. So you would get 1 over 4 times 0, which is undefined. So in this particular case, 16 makes the integral undefined, even though it may not look at it if you're just kind of rushing through it. If you stop for a minute and think about the interval, think about the function, you will soon realize that 16 cannot be evaluated, and so this is an improper integral. So we'll do our limit thing. I'm going to use b since it's the top limit, and I'm going to do 1 over square root of x, square root of x minus 4. So that's our integral, and I need to put here from 1 to b. Right. So instead of going from 1 to 16, I'm going from 1 to b, and b is the thing that's getting closer and closer and closer to 16. Tried to fix it, and then I messed it up, of course. Okay, b. All right, so how do we anti-differentiate 1 over square root of x, square root of x minus 4? This is not on our integration formulas, right? So on our formula sheet. So we have to use one of our integration techniques to be able to do this. And substitution works very nicely. If you've been practicing substitution, you may recognize this kind of problem. There are some square root things in the denominator. I want to use my u substitution to simplify this. So I typically make u a complicated thing to get rid of. In this case, I'll make u is equal to the square root of x minus 4, because that's more complicated than the square root of x. And this is the same thing as x minus 4 to the 1/2, by the way. And I compute my du dx, and that's a 1/2 x minus 4 to the minus 1/2 times 1. Why is there a times 1? Because I have to chain rule. If it's not just x to the 1/2, I have to multiply by the derivative of that inside function, as some people call it. But in this case, it doesn't really matter because the derivative of x minus 4 is just 1. All right, so this, if I solve for dx, I get dx. I'm going to move the dx further. I get 2 du, and then I get this hold on one sec. Okay, I got really confused for a moment because this was not at all coming out, and I realized I wrote this wrong. So this tells you to don't make my mistake and be sloppy with your writing. The original problem has the x under the square root and not the minus 4. And you can see that in my calculation right here. I have 16, which was what I plugged in for x, minus 4. But when I started writing it, this little squirt sign kind of started going further. And then I just kind of assumed it was going all the way. So my bad handwriting made me very confused and then very nervous that I was doing things wrong. So this is square root x minus 4. Only the x is being square rooted. So this is not x minus 4 to the 1/2. This is x to the 1/2 minus 4. All right, so I found my mistake. As you know, I don't mind making them, but I do like finding them. So let me redo my derivative correctly because I had to change what the function we're actually differentiating is. So this right here, square root x minus 4. If you spotted that, very nice. So that's what the correct substitution should be. This is still definitely the more complicated version, square root of x minus 4. Okay, so the derivative, there's no more chain rule because there's nothing else but just x in here. X to the 1/2 has a derivative of 1/2 x to the minus 1/2. And the derivative of minus 4 is just 0 because it's just a constant being added on. Okay. So this means now if I solve for dx, I'm going to get 2 times x to the 1/2 times du. All right, so I know my version for dx to plug in. I know my version for u to plug in. Let me complete this integration here. I got 1 on the top. I got square root of x on the bottom. And this square root of x minus 4, this creature right here, well, that's what we made u be. So this is 1 over square root of x times u. And I know what dx is. Dx is this guy right here. So instead of dx, I'm going to put in 2x to the 1/2 du. Okay, and then you might see that there's a x to the 1/2 on the top and a square root of x, which is the same as x to the 1/2 on the bottom. And so those are going to divide out. So what does this give me? This gives me not enough space. Okay. This gives me limit b approaches 16, 1. No, I'm doing the antiderivative. Oh yeah, no, I'm going to simplify this before I do the antiderivative. So what I got? I have 1 on the top. I just have a 2 on the top. I have a 2 du, and on the bottom I have a u. Okay, the 2 I don't have to worry about because that's just like a number that's being multiplied, so I can take it on the outside. And then the antiderivative of 1 over u is just ln of u. And I'm going from, boy, I'm getting nervous because I made those mistakes. I shouldn't do that. I'm going from 1 to b, and I wrote this as 1 to 16. Okay, so let me change that to a 16 or to a b because b is heading to 16, so that's got to be b up there. All right, so this has got to be b here. There we go. And then we're going from x equals 1 to x equals b. Okay, so I have to put, now these, remember, these are x values. These are not u values. So a lot of times I write x's here. I didn't do it this time. Let me go back and do it because remember, we used a substitution to put it into u. So we could like do the antiderivative, but we need to plug these numbers in for x. These are x values, not u values. And we know what u is. It's the square root of x minus 4. So we're going to write this as 2 ln of square root of x minus 4 from 1 to b. Now I plug in the numbers, b and 1. So I get 2. If I plug in 16, I get ln of square root 16 minus 4. And I plug in 1, I get ln of square root 1 minus 4. So I plug in my two limits, and then I have to find out what happens as b tends to 16, right? B is getting closer and closer and closer to 16. So, okay. I put 16 in there already. Oh my gosh. So I mean, I knew what I was doing in my mind, but my hand didn't cooperate. So I got to put 16 in there because I'm taking the limit. I think people knew what I was doing, but let me make it look nice. There we go. And then square root of 1, by the way, is just 1, like that. All right. So the square root of 16 is 4. So we end up with the ln of 4 minus 4, which is the ln of 0. And again, if you remember your precalculus, your ln functions, ln of 0 is undefined. It's sort of like negative infinity. All log functions look like this. They have an asymptote at 0, at x equals 0. So this is the log function, and ln of 0, if you remember, is undefined. All right, so this thing, when we do our limit, does not add up to a number. So our answer for this problem is this guy diverges. All right, I'm going to try to slow down a little bit so I don't make any of these goofy little mistakes on my next example problem. All right, so I have E here. And what's the little tricky thing that I did about E? Why did I choose E as an example? You may be wondering, how is this trickier? As I did say, do get a little trickier as we go along. So E, if you think about 0, 0 minus 8 to the negative 1/3. Now you're wondering, well, maybe that's like undefined. But negative 8 to the negative 1/3 is fine. I can write this integral as 1 over x minus 8 to the 1/3. And when I plug in 0, I get to the 1/3. And when I plug in 0, I get negative 8 to the 1/3. And negative 8 to the 1/3 is just the cube root of negative 8, which is just negative 2. So that's not undefined. When I plug in 9, I get 9 minus 8, which is 1. And 1 to the 1/3 is fine. There doesn't seem to be a problem. 0 is not a problem. 9 is not a problem. But you may have realized the problem really isn't always the 0 or the 9. It's what makes the function undefined. So what makes this function undefined? That's the question we need to be asking ourselves. And what makes this function undefined is if you divide by 0, right? Do we do 1 over 0? That's the thing we need to be thinking about. So what would the number for x be in order for make that a divided by 0 problem? Well, actually, that have to be 8. If x is 8, we have 8 minus 8, which is 0, and we would have 1 over 0. And 8 is in our interval. 8 is in the interval from 0 to 9, so somewhere hidden in there is definitely a problem when x equals 8. So we need to use a limit here. But the problem is the AB thing is sort of in the middle, so how do we do this? Essentially, what we do is we break this thing up into two integrals going with 8 in the middle. So what we do is we write this going from 0 to 8 of our function and then we add on the 8 to 9 part. So it's just basically, we're going to go from 0 to 8, find the area, go from 8 to 9, find the area, and add them up. That'll be the total area, of course, if the area actually exists. So we break this up into two parts. Each of these is going to have a limit. Let me switch colors. So I get limit. In this case, 8's the problem. So I'll do x approaches b from 0 to b of 1 over x minus 8 to the 1/3. And then this one, the 8's a problem down here. So I'll say the limit as a approaches 8. And this one here is going to be 1 over x minus 8 to the 1/3. Now I'm going to take you back to a little bit of calculus 1. So if you remember in calculus 1, it depends whether we're taking a limit from the left, a limit from the right, or a limit from both sides. On this first part of the interval from 0 to 8, we're going from 0 up to 8. We're only approaching 8 from the left-hand side. So this is the limit as x approaches I'm just going to try to make no mistakes. And there it made a mistake right there. So this is b approaches 8. So we're only getting closer and closer to 8 from the left-hand side. So we write a little minus right here. We're getting closer and closer and closer to b, getting closer and closer and closer to 8 from the left-hand side. On the limit over here, we're going from 8 to 9. And I don't have my integral symbol. Boy, these last few videos, I've made a lot of mistakes. I need to slow down. I guess I'm too worried about time. But I don't want these videos to be forever. So this is B, no, this is 8 to A, like that. Okay, so that's my interval. It goes from 0 to B, where B is getting closer and closer to 8, and then it goes from A to 9, like that. Yes. And because we're going to 8 to 9, our 8 isn't coming from the left. Our interval's 8 to 9. So 8 is only considered for numbers bigger than 8. So we go 8 to 9. So we're going to do a limit from the right-hand side for this guy right here. Okay. Straighten it all out. Probably. Okay. So now we need to compute these two limits and integrals. We get 1 over x minus 8 to the 1/3. We're going to do this using a u substitution. We're going to get rid of that x minus 8. And fortunately, du and dx are the same. So these end up being much easier to differentiate with a very simple u substitution. All right, let me try again. Limit b approaches 8 from the left-hand side. And we're going from 0 to b, like 0 to 8. And then we get 1 over u du. And we're going to add to that the limit. And this time we're going from 8 to 9, which is going to be a to 9. So this is the time we're going to use 8 from the right-hand side. And we have our interval, our integral from a to 9 of 1 over u du. Right, so we're going from 0 to 8, but we can't put 8 in there, so we put like b approaching 8 from the left. And then we go the integral from 8 to 9, but we can't put an 8 in there. So we put a, which is approaching 8 from the right-hand side. The substitution is the same both times because x minus 8 was the same. So now we can just do the antiderivative of these guys. Okay, let's see what I get. B approaches 8. And the integral of 1 over u is just ln u. And we're going to go from, this is x equals 0 to x equals b. And then I'm going to add in this other limit. And we still get ln u. And this time we're going to go from x equals a to x equals 9. where a is getting closer and closer to 8. Now, once again, you have to put these back in terms of the variable that you're actually using in this problem, which is x. So we get our limit as b approaches 8 from the left. We get ln of b. We have to put in what u is. What's u? Oh, u is this thing right here. U is x minus 8. Okay, so we get x minus 8. All right, and then we get x equals 0 to x equals 8. And then we get plus this limit thing. And then we got to put back in u ln of x minus 8. And this one's going from a to 9, like 8 to 9, but we can't put an 8 in there because it makes it undefined. Okay, so now we plug in the numbers. We're almost done, I assure you. If I plug in, this is a b up here, right? If I plug in b, oh no, that's an 8. Is that, yeah, no, that's a b. That's a b. I get ln of b minus 8 minus ln of 0 minus 8. And over here, I have the limit as a approaches 8 from the other side. That's supposed to be an arrow. And then I'm going to get, when I plug in 9 and a. So I plug in 9, I get ln of 9 minus 8 minus ln of a minus 8. Okay. So now I actually do the limits. We're going to find very quickly that this limit cannot be computed. The reason is because when I plug in 8 or something infinitesimally close to 8, this thing right here is going to ln of 0, because 8 minus 8 is 0, and ln of 0 is undefined. So I don't care what you try to add to this, it's going to be undefined, right? Undefined plus 7 is still undefined. So without even doing the rest of this thing, we know the answer to this integral problem is undefined. So this thing right here is undefined. And the reason why we know this is true is because we split this up into two integrals, and we used limits to evaluate those integrals. The first one from 0 to 8 didn't even exist, so we know that the integral diverges. And I wrote undefined here. You may realize that I need to write out the word diverges here. Because it's undefined, we have to use our limits, but because the area is not finite, it's not a number, we say diverges. Okay, and so what I thought might make this problem trickier was that where the function was undefined was not clear, because it wasn't at 0, it wasn't at 9, it was somewhere hidden in between. So you're going to have to be a little bit careful about those kinds of problems where you have a definite integral and it's not obvious where the limit is unless you stop and do a little investigating and saying, okay, what could make this undefined? 8 makes it undefined. Is 8 part of our interval? Yes, it is. 8 is part of our interval from 0 to 9. So this is an improper integral, and I have to use my voodoo, my improper integral limits to be able to find it. All right, got 2 more examples for you in this video. Hopefully they go more smoothly than the last one. I keep saying that. It'll eventually become true, right? If I make enough predictions, eventually it'll come out right. This one goes from 0 to infinity. Cosine, by the way, is a graph, a function that just goes up and down and up and down and up and down. There's no undefined parts to the cosine graph, but we cannot plug in infinity, right? Infinity is not something we're allowed to plug into any function because infinity is not even a number. That's what's going to make this thing like not calculable or the function undefined. But we know what to do with this situation. We just do the limit Infinity is the problem, so we do b to infinity. And then we're going to do the antiderivative from 0 to b of cosine x dx. So far, so good. Nothing really that shocking. We needed to replace the infinity by a b. We've done that several times before, so nothing quite new yet. So what do we get? We get the limit as b goes to infinity. The antiderivative of cosine is well known. It's just sine. So again, nothing special about the integration. And I go from 0 to b. This is x equals 0 to x equals b. And now I just plug stuff in. So I'm going to get the limit as b approaches infinity. I plug in b, I get sine of b. And I plug in 0, I get sine of 0. And so this is what my limit is. My limit as b approaches infinity of sine b minus sine 0. Well, sine 0 is a number. Sine 0 is 0, actually. So we know what that is. But what happens with sine b? So the reason why I chose this problem to talk about was that I'm trying to hit the limit as b approaches infinity of sine b. And that is not infinity. All right. The sine of infinity is not infinity. Sine is like cosine. Remember, cosine wiggles up and down. This guy is the cosine graph. But if I was to graph the sine graph, it's a very similar wave. It just starts here at the midline. This is y equals sine, and it never goes above 1 or below -1. All right. So the y values or the function values never go to infinity. That's not an issue. So what does this limit is? Well, if we go off to infinity for the sine graph, we never get a number. It's just up and down and up and down and up and down. There's all the numbers, the infinite numbers between -1 and 1, and they just keep repeating themselves over and over and over again. So even though this is not infinite, it still diverges. The reason why is because there's no number, there's no finite area that we can say what's equal to, right? There's a range of areas, but that's not a specific finite area. So this diverges. So I chose this problem to show you that you can have an improper integral that diverges, but not because the area is infinitely big. It's just because we cannot calculate the area. There's no way to calculate this area because it keeps going up and down and up and down and up and down forever. All right, so that was the reason behind example F. And my last example, which is G here. Let me zoom in a little bit, make this easier to see. The reason I chose example G is because it has infinity on the top and the bottom limit. And like what you do with that kind of situation. We know we can't plug in infinity because it's not a number. We can plug into any function. So we need a placeholder, but we also need a placeholder for negative infinity. So this is again where you're going to split it up into two integral parts and find the integral of each of those parts and then add them together. So we're going to pick something in the middle. You can pick 7 in the middle. A lot of people pick 0 in the middle because it's kind of symmetrical in a way. But honestly, you just need to break it into 2 parts, whatever you want. I'll go from, let's say, instead of negative infinity, I'll write a, and I'll have a tend to negative infinity. And I'll choose something in the middle like 0. And here's my function. And then I'll do another limit. And this time I'll go from 0 to positive infinity, but I'll write a b there instead of infinity. And then I get the same function. So I want to show you this example to give you an idea of like what do you happen when there's like definitely lots of places where the function is undefined. By the way, there's no divided by 0 in this problem. That's something that if you were thinking about, fantastic, great job. The bottom is x squared plus 1. And the only time x squared plus 1 could equal 0 is if you use x is equal to I, like a complex number, which we don't do complex calculus in calculus 2. So that's not an issue for this problem. We're not going to have any 0 in the denominator for any real value of x. So now we need to do our integral and figure out our limits and figure out if this thing converges or diverges. This is another example of a u substitution where we can let u be the x squared plus 1 thing on the bottom, and then du dx is equal to 2x. Or more specifically, we get dx is equal to du over 2x. And we can put those into both of them are going to have the same substitution because they're really the same integral. So we can do it for both of them. All right, so we get the limit a approaches negative infinity, a to 0, x over this u thing that's being squared, dx is du over 2x. And then our second integral is going to be basically identical, except the limit is different. And we get x over u squared. Remember, x squared plus 1 is u, so I get u squared. And then dx is still du over 2x. All right, both of these are going to simplify in a very similar way. I can bring the 2 on the outside. So let me just scooch this over a little bit. A approaches negative infinity. So I'm going to bring the 1/2 on the outside. And then I end up with the x's dividing out. And I have du over u squared. And over here, I have the same thing. And the x's divide out. And instead of u squared, I'm going to remind you that's u to the negative 2, right? U squared, or u squared in the denominator is u to the negative 2. And I'm writing it that way just to remind you how we can anti-differentiate this just by using the power rule. We just add 1 to the exponent, etc. Oh, that's not x, it's a. Keep my straight. And this one's going to be the b thing. And the antiderivative of u to the negative 1 is u to the negative 1 over negative 1 from 0 to b. These are x values. And this can be the same thing. So it's going to be u to the negative 1 over negative 1. And I have values from a to 0. This is x equals a to x equals 0. All right, let's not forget our 1/2 in front of both of these guys. Oh, I forgot the 1/2 over here. So there's the 1/2 over here. Almost forgot it. There we go. So the 1/2 came from like the fact that only the x's divided out, and there was a 2 left over. I just forgot to put the 1 over 2 on the outside. Okie dokie, we're almost done. We're almost done. We're almost done. So let me just switch colors. I have the limit as a approaches negative infinity of negative infinity of 1/2. Now I got to put u back because I can't plug x equals something into a u thing. U is x squared plus 1. So I'll put x squared plus 1 there. So in fact, I'll combine the negative 1 with the negative 1/2. And I'll make this 1 over x squared plus 1. All right, because it's u to the minus 1. So u is this guy right here. Remember, that was our substitution. So u to the minus 1, just to help you with the visualization, is just 1 over x squared plus 1, right? It's the upside down version of that. So I get u to the minus 1, which is 1 over x squared plus 1. I just merged the negative 1 and the 1/2 together. And then I'll do the same thing over here. I get the negative and the 1/2. And I get 1 over x squared plus 1. The first guy goes from a to 0, and the second guy goes from 0 to b. So now I have to do my plugging in stuff. Negative 1/2. I got to plug in the top limit first. Top limit is 0, so I get 1 over 1. And then I plug in the bottom limit, which is 1 over a squared plus 1. Boom. And then I get plus this minus 1/2. Oops, I need my limit. forgot my limit up here too. I did warn you in the beginning of this video not to forget to write your limits. So I was just demonstrating that for this problem here. Limit as b goes to infinity. All right, so I still do my limit as b goes to infinity. I got my -1/2. I got to plug in b first. So I get 1 over b squared plus 1. And then I got to plug in 0. And I get 1 over 0 squared plus 1 is just 1. So like that. Okay, so what happens when I plug in negative infinity? Remember, a is approaching negative infinity. Here's where an a is. There's no a in that first guy. So this is just going to be 1, right? It's not going to be anything different. So what do I have here? I have 1 over a squared plus 1. Negative infinity squared is going to be infinity, positive infinity, or something like that. And 1 over infinity, 1 over infinitely large number from your Calculus 1 class is 0. So this goes to 0 because you have 1 divided by infinity, which is going to be 0.00. It's going to be 0. It's going to be the most infinitely small number possible. And over here, we get -1/2. B is going to infinity. And once again, you got 1 over something infinitely large. Infinity squared plus 1 is infinity. 1 over infinity is 0. And 1 over 1 is just 1. So I don't have any problem with calculating this thing. So this is definitely going to converge. Let's see what number it converges to. It converges to, well, this we get -1/2 times 1, which is -1/2. And over here, we get -1/2 times -1, which is +1/2. So it looks like -1/2 plus +1/2 is equal to 0. So this converges. The integral converges. It has a finite area. Has a finite area of 0. How is that possible? How could something have an area of 0? Like I did all the math right, I believe. The reason why is because this function, maybe I'll pause and show it to you on Desmos. This function has equal parts above the axis and below the axis. So if it has a area above the axis, this is a positive area, and an area below the axis is a negative area. And if they're exactly the same, then the positive amount of the area and the negative amount of area are going to subtract off and equal 0. All right, let me pause and then I'll show you the video at the graph at the end of the video. Okay, so I graphed the video on Desmos. There's the function x over x squared plus 1 squared. And you can see it's just symmetrical, right? So we have a positive area up here, a negative area down here. They're exactly the same, except, different signs. And so when I add up all of this positive area and all this negative area, I really do get 0. So this total area is finite. It's equal to 0. And so we say the integral converges. Okay, so that was my tour through improper integration, improper integrals using limits. So please let me know if you need any more assistance with this material, or if you have any other questions. Hopefully you found this video helpful, and you reach out if you have any questions. And of course, always have an enjoyable